Welcome, welcome folks to 8.3. We're starting out with number 5. Here we have a regular polygon. The central angle measures 30 degrees. If each side of the regular polygon measures 5.7 degrees, I want to find the perimeter of the polygon. So the thing that is quintessential here is that we understand we have a regular polygon and the central angle is 30 degrees. So I'm going to just draw like kind of a, I don't know, like a squiggly circle thing. So this squiggly circle thing is meant to represent a polygon, but I don't know how many sides this thing has because it would be very important for me to know how many sides. That way I'm able to figure out what the actual perimeter is going to be. Because I know each side length is going to be the same because it's a regular polygon, and I know the central angle. So now I want to use some information, which is that this little bit right here, there we go. So this angle here is 30 degrees. Now, why is that important? That's important because the regular polygon has all of the same central angles out like this. I'm trying to draw a decent picture. I don't know how good it is, but okay, so this is a bad picture. I'm just drawing like this thing out. So don't look at this and think like, oh, this thing is definitely a hexagon or whatever. So as I look at this, if I've got my central angle given to me, I'm able to determine the number of sides. Again, the picture is not actually representing the number of sides here, just me drawing a picture. So if each central angle is 30 degrees, then let's figure it out. The total in the middle here is 360, right? That's my full circle. If I divide this by 30, I'm going to get the total number of central angles that I have in this figure. That's going to also give me the number of sides. So in this problem right here, I just do 360 divided by 30, and I get 12. So my n here equals 12. So if I could do a better job drawing, which I don't think that I can, I would like go from midpoint, on each of these, and there would actually be 12 sides. I don't think for a second that I can do that accurately, so I'm not even going to attempt it. So now that I have each of these things as 12 sides, I'm going to say, okay, well, I was told that my side length, why do I keep doing that? There we go. So I'm told that my side length here equals 5.7. I have 12 sides. Let's do some math, and we do 5.7 times 12, and we get 68.4, and this is my perimeter. Any questions on number 5? Cool. Let's look at number 7 here. So looking at this one here, we have a regular hexagon. So again, the common theme here, all regular polygons. So regular hexagon, the length of the apothem is 10 centimeters. I want to find the length of the radius for the circumscribed circle. So circumscribed circle for this hexagon means it's on the outside. So I want to think about what this means. I hope I have a hexagon. I do. Oh, it's my lucky day. This is my circumscribed circle. Let me grab this here. Pretty spot on. Excellent. Man, I am loving the paint tools right now. So again, regular hexagon means all my lengths are the same. The apothem is told to me to be 10. So as I look at this thing, this distance from the center out to the midpoint on the side is 10. Cool. I want to find the length, the radius of the circumscribed circle. So what I'm looking for is this thing right here. So that's the distance I want. And what would we call this? We call this the radius of this thing. So now, as I'm looking at this, I'm saying, okay, well, if my apothem is 10 and I have a hexagon, I should be able to pull a little bit of information from my hexagon to be able to solve this problem. Again, once we learn some more trig stuff, we wouldn't need that. But for right now, we do. So let's think about what my central angle would be for a hexagon. So for here, this central angle created would be 60 degrees. So I'm now going to just isolate this triangle. If this is 60 degrees and these two base angles are going to be congruent, of the 120 degrees available, I'm going to split it into 60 and 60. So now I have an equilateral triangle, and this always happens when we have a hexagon, so regular hexagon, that is. So if you remember, I don't know, in school, if you guys had like some of those little blocks, a lot of times you'll get like the hexagon and you get the equilateral triangle, and you can fit 6 of those triangles perfectly into the hexagon. So that's this sort of concept coming into play here. So now I'm saying, well, I have this line down the middle here, and I know that this is 10. And this is going to split my triangle into a specific right triangle, which we really like to work with. So the triangle that I end up creating ends up being a 30, 60, 90. So this angle up here, which used to be 60, is now 30. Here I've dropped my altitude down through, this is my intersection line from here. So this is 90, and now this is 60. The length that I know is the apothem right here is 10. Well, if this is 10, as it relates to my triangle, again, across from my 60 is my x root 3. My goal is to figure out what this length is right here. So I need 2x. So this is 2x, and this is just x. So now, if this is x root 3, I can solve for my x value by dividing by root 3. So I'm going to divide by root 3, and I want to rationalize this thing. To rationalize it, I'm going to multiply it by a clever 1, which is root 3 over root 3. By doing that, I get 10 root 3 over 3. And that is my x value. So why is that important? That's important because I want to use that x value right up here. So I'm going to take 2 times x, which would be 20 root 3 over 3. So this is my distance for the radius of this thing to the circumscribed circle. So this is on the outside. If I said I had a circle inscribed in the hexagon here, then it would actually be reaching its, I don't know, the circle itself just reaches and touches at each of these apothem points as a tangent. So if we put another circle inside, it'd be using apothem, but on the outside, it's using radius. Any
Mr.
questions
Street,
on this one?
how do you know R is 2x?
Because in a 30, 60, 90 triangle, opposite the 90 is always 2x.
Cool.
Good question. Yeah, those 30, 60, 90 triangles and the 45, 45, 90 triangles come up all the time, especially because you guys don't know trig. So like as of right now, you're a little bit, I mean, just a smidge handicapped in terms of what you can deal with in terms of triangles because you don't know the trig stuff, but we'll get to the trig stuff. So basically, we'll just see again and again, the only triangles that keep popping up are 30, 60, 90 and 45, 45, 90. Good question. Any other questions on 7? Perfect. Let's look at number 9. So in a particular type of regular polygon, so it's not telling us how many sides, the length of the radius is exactly the same as the length of a side of the polygon. What type of regular polygon is it? So just having done number 7 here, I want to think about this for a second. So let's just zoom up a little bit to what we're just doing, which is number 7. So this question asks, a particular type of regular polygon. Is it an equilateral triangle? Is it a square? Is it maybe a hexagon? Is it a pentagon, right? So when I'm looking at this, the apothem is going to be the same, or should be, the radius is the same length as the side. So when I'm looking at this, what did we just figure out here? The radius was the same as one of these side lengths because this is an equilateral triangle. So just like we figured out this part here was my 20 root 3 over 3, this over here is 20 root 3 over 3, and this is 20 root 3 over 3. So here I see my radius is the same as my side length. Therefore, the answer here is how the wizard removes a curse, hexagon. Any questions on 9? And that's a regular hexagon, of course.
Very funny.
Thank you. I try. In my mind, when all of you are muted, you're all dying laughing, so it works out well.
Oh, we are.
Yeah, oh, I know, for sure. 23, I have the area of an equilateral triangle whose radius measures 10. There are a multitude of different ways to approach this problem. Let's look at one of them. Here I have a nice equilateral triangle, or at least it looks, fairly equilateral. When we're talking about the radius of an equilateral triangle, this thing is saying, okay, from the center out to one of the vertices. So let's draw our center point here. And now let's draw just one radii out. Actually, let's do our radii in another color here. Let's do an orange. So there we go. There we go. There we go. So these are the radii of the triangle. Now it may seem a little bit weird to think of radius in terms of like different polygons, like a triangle or a square or whatever, but each of these polygons does have a radius, as long as they're a regular polygon, because they're going to intersect at a point on a circle that would be circumscribed about it. So imagine if I put the circle outside of this thing, then I would imagine it as a radius. So I guess I can draw that in so we don't have to use our imagination. We have paint for that. That's pretty close. Perfect. Anybody identify the symbol here? I think that's Mercedes. So when we look at this, I'm basically saying, okay, well, this orange is my radii, and this is my radii, and this is my radii. So now if I want to figure out something about this triangle, I'm going to be using that information. And I also want to keep in mind, I know some 30, 60, 90 triangle stuff. When I look at this equilateral triangle, there's a multitude of ways of figuring this thing out. But I personally would think of it in terms of, let's continue to drop down in altitude here. And let's split one of these triangles. So as I look at this thing here, I'm saying, okay, well, if this internal angle here, so again, I have 360 being split into 3 parts. Each of these parts is going to be 120 degrees. So if this is 120 degrees, and then I just bisected it to drop this altitude down, then now this is a 60, and this is a 60. From there, this is 90, which leaves this to be 30. I'm now going to highlight this new triangle that I have here. I think there's a nice one that I can do it. There we go. So let's talk about this. We are given this length here was 10. This is my right angle. This is my 60. This is my 30. This is always 2x, which is nice. So 2x goes here. Here I have my x value. Here I have x root 3. So if if 2x is 10, that means x equals 5. And that means x root 3 is 5 root 3. So now I just figured out that this chunk from here to here is 5 root 3. If this is 5 root 3, I'm able to figure out the side length of my triangle. So when I'm looking at my triangle here, I can say the side length equals 10 square root 3. From here, I know there's a way that I can figure out the area of my triangle, if it's an equilateral triangle that is, just based off the side length. That formula is area equals side length squared over 4 times square root 3. So I personally would use this, but again, you don't need to. One other way of solving this thing is I can look at this and I now have defined the full height of this triangle, and I have a full base of this triangle. So my base now here again would be 10 root 3. So from here over to here is 10 root 3. And I know the height of this part here is 5. And then the height here is the radius, which is 10. So another way that I could do this is I could just do 1/2 base times height. So that's another easy way of setting this one up. Area equals 1/2. My base, which is 10 root 3. I don't know why my roots are not coming out so nice here. And then times my 15. So either way you want to solve it is fine. I personally probably would do it this way, but if you want to set it up this way as well, that's fine. So I'll just show it on the bottom. 1/2 of 10 is 5. So here I have 5 root 3 times 15. Last time I checked was 75 root 3. If I want to do it on top here, when I take 10 root 3 and I square it, I get 10 squared times 3. Here I've got all divided by 4 times my root 3. 10 squared is 100, divided by 4 is 25, times 3 is 75, and then my square root 3 just riding along. So again, either way you do it, end up at the same spot. You could do Heron's formula if you're a madman and you really want to go that route, but I wouldn't recommend it. Any questions on this one? Those would be the two major ways I would say most people would solve it. Another version of solving this would be you could solve for the kind of smaller triangle down here, and you could either do as this little one, or you could do the slightly larger, I would say maybe medium-sized triangle. If you found just this little one, you could do 1/2 base times height here, and you just multiply it by 6. Or you could just do the small one, and then you multiply by 3. So right there, there's like 5 or 6 different ways to solve this problem. So again, it's just a lot of kind of knowing what tools are available. The real crux of this problem, the thing we needed to be able to figure out, was that I could draw this as 120 and drop an altitude down through. Good question. Any questions on 23? Perfect. Take a peek at 29 here. So here we have a regular polygon of 12 sides. There's no way I can draw that thing. The measure of each side is 2 inches. The measure of the apothem is exactly 2 plus √3. Okay, find the area of this regular polygon. Well, easy enough. I have a formula that tells me the area of all my regular polygons, and that is 1/2 my apothem times my perimeter. So now I'm going to fill in the bit that I know, which is that I've got 12 sides, and each side is 2 inches. So my perimeter is going to equal 12 times 2, 24, and we'll throw that in right here. And then I'm given my apothem, which is 2 plus √3. Please just keep in mind that the 2 and the √3 cannot be added, so we're going to leave it as 2 plus √3, albeit a little squish there. And here's my 1/2. So now I'm just going to do the multiplication. So personally, I would do 1/2 times my 24, and that's going to give me 12. And then I would do 12 times each of these things. That's just how I think about it. If you want to do it differently, whatever floats your boat. So 12 now times 2 is 24, and then 12 times √3. Whoopsie. There's my final answer. Any questions on 29? Perfect. So really, I mean, the big things I care about are, can I find the perimeter, and then do I know the apothem? And if I'm able to figure out the number of sides and the side length, then yes, I can figure out perimeter, and from there I'm good to go. 31 here, which I think will wrap up 8.3, yep. So here we want to find the ratio of the area of a square circumscribed about a circle to the area of a square inscribed in the circle. So this is a bit of a mind game in terms of what's going on here descriptively. So let's draw a picture. So here I've got a sweet circle. Actually, let's use different colors here. So here I've got, what I will have is a square. Close enough. And then I've got another square inside of this circle here. There's a couple ways of drawing this. So I'm drawing it like this. I'm going to draw one more version of the square, which is that it's going to look like this. And it doesn't matter which version you use. So just keep in mind that I've only got one green square. I'm just drawing it in 2 different orientations. The reason I'm drawing it in 2 different orientations is that I think probably for most people, it's a little bit easier to see it tilted on its side like this, but you don't have to solve the problem that way. So I'm going to solve the problem that way. Again, you don't personally need to. So now I'm going to put a big green dot in the middle here. Pretty cool looking picture. So now when I'm looking at this thing, I'm saying, okay, find the ratio of the area of the square circumscribed about the circle to the area of the square inscribed in the circle. So basically what I'm looking for here is area of red square, and then that's all divided by green going. area of my green square. So that's my goal, is to just do that number divided by that number, and that's my ratio. So that's the goal. So to figure that out, I just need to find the area of the red square. Now I don't have like a set distance here, nor do I really need one because again, it's just a ratio. So it really doesn't matter like what the actual length is. So I'm just gonna start by naming a radius of my inner green square. So lots of different ways you can do this. This is just the way that I think of doing it. So I'm gonna name this length. I don't know that I wanna do it in green. That's gonna be too much green. Let's do it in blue. No, I've already got blue, purple. So as I look at this one here, I'm looking at the radius now of that small green square. So here I've got my small green square. As I do that, I create a right angle here, although we don't necessarily need that. We could use it. So I'm just gonna say this is little r and this is little r. Okay, cool. So I've got little r, I don't know, I'll throw a right angle there, why not? So now as I'm looking at this thing, I'm saying, okay, well, if this is little r, how does that relate to the bigger square? Well, this little r is defined, oops, I don't want to do that. So it's defined by radius here, and I could find the area that way, but basically what I'm saying is that if I were to continue this radius across, which I don't know why I didn't do in the first place, right? The radius of the square is now the full side length of the bigger square. So I'm gonna just write that out. So my diameter of green square is side length of red square. Hopefully I don't do any typos, but odds are I probably will. Diameter of green square is length of red square. Cool. So here's a little note for myself. So now if I wanted to relate these things, I could start talking about the length here on the bottom as being 2r. So now if I want to talk about the area of the red square, it's going to be 2, what the heck kind of r is that? There we go, 2r squared divided by, and now I got to figure out the area of the green. So for the area of the green, there's a couple different ways we can do this. Personally, again, I would just say, well, this is r, this is r, this is a right angle, so I know this is going to be r root 2 right here for this hypotenuse. If you want to go through and do out the work for it, you can, but again, this is a 45, 45, 90 triangle. So I'm going to just jump to that. So I'm going to erase a little bit of the other green square just so people can kind of focus in on the one that I am using. There we go. So again, using this triangle here, and I'm determining the side length of the green square. The side length of the green square is r root 2. So here, I'm going to be doing r root 2 squared for the area of this thing. Now, when I am doing this, I can drop the squares if I wanted to, because I'm squaring and squaring. It's going to just unsquare itself, but that's okay, because I'm squaring the whole thing, so I'm just squaring the ratio. But let's just do it out. So let's call this 4r squared. On the bottom here, when I square root 2, it gives me 2. So now I have 2r squared. This is what I'm talking about, that these things will cancel off. So let's just get rid of the r squared. My ratio is 4 to 2, which is really just 2 to 1. So final answer here, the ratio would be 2 to 1. Pretty cool. Any questions on 31? Alrighty. Oh,
How did you get from r root 2 squared to 2r squared?
so
Never mind, I see that now.
you see it
I
now? Okay.
yeah.
So when we're given a value like this, I'll just write it out for others because I'm sure there's at least one other person that was confused on that. So here we got r root 2 times r root 2. Here we got r, and r gives me r squared. And then I've got my root 2 times root 2, which is just 2.
For some reason I was thinking that the r was the part that was underneath the square root.
Oh yeah, no worries. Does that make sense?
Yeah, it makes sense now.
Perfect, perfect. Yeah, and that's coming from this right triangle the 45, 45, 90 here. Perfect. Any other questions on 31
Wait,
or
I'm
anything
sorry.
8.3?
Where is the R root 2 coming from? I'm a little confused.
So the R root 2 is coming from this triangle right here from within the green square. So I'll isolate it here for you. So this is the green square, and then I drew my radii out. So I had a radius like, oh wow, well whatever, I can use this as long as I stay relatively straight. There we go. So there's my radius and my radius drawn out. So we said this was R and this was R. And if this is R and this is R, and I know this is a 90 because this is my square being split into fourths, then what's going to be this side length here? Well, this is a 45, 45, 90. So I know this is my quote unquote X value. This is my quote unquote X value, and this is my X root 2. So if my X value is R, then this turns into R root 2.
Oh, okay, okay.
Good question. What else we got? Alrighty. I will wrap up the recording here.